Nanomaterials developed by various processes at ARCI, Hyderabad. Nano is too small to be seen by naked eyes. We can see human hair. Red blood cells can be seen under optical microscope but not the DNA in it. DNA strand is made up of carbon-based molecules. One carbon atom is smaller than 1 nanometer and can be seen only under high-resolution electron microscope. Nature knows nanotechnology much before man. Let's see some examples. Extremely fine features on the toes of insects make them very sticky and hence insects do not fall from walls. Lotus leaves in water never get wet due to nanospikes on their surface. Nanoflake structure at exterior and nanoporous structure in the interior make the beak very strong and light. Nanometer-sized biodegradable threads of spider silk are stronger by weight than high-tensile steel. It is also elastic enough to stretch up to 10 times its initial length. Vibrant colors in butterflies and insects are due to the light scattering of ultrafine features on their wings. Bioluminescence in fireflies and jellyfishes is at nanoscale. Does small size really make any difference? Paper catches fire faster than log of wood from which it is made up of. Powdered sugar is dissolved faster than crystal sugar. So size does matter for the properties of materials. Then what is the size below which the material properties are altered? The small features which contain the smaller number of atoms or molecules than 1 mole. This number is different in different materials. The change in properties due to nanosize can be understood by the fact that, as the matter is cut into smaller pieces, the surface area increase largely. And the ratio of number of atoms present on the surface to that in the interior goes on increasing. This leads to change in all the chemical and physical properties such as melting point, density, surface charge, thermal, electrical conductivity, etc. As per electronic band theory, metals, insulators, and semiconductors are the 3 types of materials. Semiconductors have an energy gap between valence and conduction band which is called as a band gap. The electromagnetic wave having energy equivalent to the band gap excites electron from valence band to conduction band, leaving behind the positive hole. Compared to the bulk semiconductor, higher excitation energy is required to excite electrons in nanoparticles. Hence, as the size of the nanoparticle decreases, the band gap increases. This influences the electronic and optical properties. For example, different sizes of cadmium selenide nanoparticles show different shades of photoluminescence. It is known that highly conducting metals have free electron cloud around the positive nuclei. When light falls on the nanoparticles which are much smaller than the wavelength of light, the electrons interacts with its electromagnetic field and start oscillating due to their collective excitation and de-excitation relative to the positive nuclei. This phenomenon is called as surface plasmon resonance. Electrons in nanoparticles of different size and shapes interact differently with range of wavelengths in the visible light, giving rise to different colors. We know that matter is 3-dimensional. When one of the dimensions is reduced to nanosize, it's called nanofilm. If 2 dimensions are nano in size, nanowire is formed, and if all the dimensions are nano in size, then these materials are called as 0-dimensional or quantum dots. Nanomaterials are made by either assembling few atoms or molecules, which is called as a bottom-up approach, or by cutting down of the bulk material to nano size, which is known as a top-down. ARCI's Center for Nanomaterials has unique facilities to produce nanosuspensions, nanopowders, nanofibers and nanoporous materials at pilot plant scale. The most popular bottom-up approach is chemical synthesis method, which can have precise control over the particle size, shape, morphology, and composition. It can create novel, self-assembled nanostructures such as nanoflowers, nanospheres, etc. A nano-silver suspension is made by chemical route. This nano-silver suspension was especially developed for applying it on textiles to make them antibacterial. The silver nanoparticles possess tremendously high surface area due to its ultrafine size. Very small amount of silver is sufficient to coat large area of textile. Various antibacterial apparel made by ARCI technology are now available in the market in several popular brands. Another suspension of Bandgap engineered semiconducting titanium dioxide nanoparticles is produced to apply on textiles to get self-cleaning and UV protection functionalities. This is based on the concept photocatalysis, in which titanium dioxide degrades organic pollutants on the surface when exposed to sunlight and keeps the surface clean. As the conventional washings of these cloths are reduced, we benefit with savings on electricity, water, and detergent. This ARCI technology is successfully commercialized. Another bottom-up approach, flame spray pyrolysis, for bulk production of oxide nanopowders, is available at ARCI. The precursor solution is prepared first and then sprayed in the tall flame, where each droplet undergoes combustion to form nanoparticles, which can further grow to form clusters or nanorods. Thus formed nanopowders are finally collected. The nanopowders of hydroxyapatite, silver-doped copper oxide and lithium iron phosphate, produced by FSP, are tested for the dental implant application, antiviral functionality, and as cathode material in lithium-ion batteries respectively. One more versatile facility, radio frequency induction plasma plant, is available at ARCI, for bulk production of metals and their carbides, nitrides, etc. In this machine, powder of bulk material or precursor liquid or reacting gas is passed to the plasma of inert gas. The cloud of material vapor is formed in the plasma. The flow of quenching gas converts this vapor into nanoparticles, which are collected in the glove box. Ultrafine, metallic, aluminium nanopowder produced in RF induction plasma plant has shown very high burning rate due to its enormous surface energy. The ignition efficiency of rocket propellant is tremendously increased by adding small quantity of nano-aluminium powder to it. Nanofibers are produced by electrospinning technique at ARCI. The machine NanoSpider can coat the nanofibers of desired functionality on long lengths of substrate such as a fabric or paper. Nanofibers are proven to give efficient filter media for air and liquids. The nanofiber-based air filters have shown large improvement in the air filtration and dust holding capacity, compared to conventional filters. ARCI is also putting efforts to give functionalized, nanofiber-based, efficient, long-life and cost-effective import substitute filter cartridge technology for endotoxin removal from the blood. The best thermal insulators, ultralight nanoporous aerogels, are produced at ARCI via supercritical drying method. First, a gel is prepared by chemical route. The liquid in the gel is then extracted at high temperature and pressure such a way that gel structure doesn't collapse. Silica aerogels have more than 95% porosity, and less than 5% solid in it. This solid is nothing but a three-dimensional, random network of less than 10 nanometer sized silica particles. Hence the heat transfer through solid is minimum. The pore size is less than 70 nanometers, which is smaller than the mean free path of air molecules at atmospheric pressure, required for molecular collision to transfer heat. Hence the convective heat transfer is highly restricted. Silica aerogel is transparent to some infrared wavelengths and radiative heat transfer is less at ambient temperature. The technology of manufacturing of silica aerogel flexible sheets for high-temperature thermal insulation was transferred for commercialization. Bulk production of nanosheets, the two-dimensional structures, are produced at ARCI in custom-designed pressure synthesis reactor. Tungsten disulfide and molybdenum disulfide nanosheets produced are proven as a lubricant and catalyst in petrochemical industry. Nanostructured thin films are produced by simple, cost-effective, spray pyrolysis deposition technique. Aerosol droplets of precursor solution are sprayed over hot substrate where reaction occurs and film grows. At ARCI, specialized films are developed for applications in sensors, photoelectrodes in hydrogen production, etc. High-energy milling, a top-down approach, is also available at ARCI for bulk production of nanostructured materials and their dispersions in metals. The imparted velocity on milling balls is very high, compared to any other milling technique. Hence the coarse particles are broken to nano size in a very short time, eliminating contamination. Cryomill is used to synthesize nanostructured materials at -190 degrees Celsius. This technique is specially used for the soft and temperature-sensitive materials like polymers and biomaterials. These materials becomes very brittle at cryo temperature, and particles can be easily broken into nanoparticles.
Team Nano at ARCI is engaged in the translational research to develop new cutting-edge technologies to make India Atmanirbhar Bharat.